classroom. And so what I thought we could do this afternoon is a little bit of sampling of all the inspiration I've benefited from over the past several years and things we've borrowed and adopted and adapted from others to give you a taste of what we do in a course called CS50 at Harvard. In the spirit of this morning, this is how we do it in university, but perhaps a bit anomalously. I dare say that this course, CS50, which is meant to be our introductory course for majors and non-majors, has focused atypically on the cultural experience that students have in the class, on the social experience, on the community aspect, and indeed, as the course has grown beyond Harvard's own boundaries to schools like Yale, a few universities abroad, to the world at large freely via edX, a MOOC platform, and now a high school audience, as you'll soon see. It's been really fun to see people from around the world truly interconnecting, both at the secondary school, university level, and beyond. So this is representative of something where we'll end, but where we'll begin, I thought, is a quick overview of what it is we do. So this is a glimpse at the first day of class, and I emphasize first day since everyone's there on the first day, but most everything we do in the classroom is filmed so that ultimately we actually have aspired to create for students an educational experience that I dare say is already or is about to be superior to experience in some forms online, which is to say the lectures, even though we do meet at such a beautiful place as this on campus, we have an entire support structure of teaching fellows, as we call them, and course assistants, who are the ones on the ground working with students one-on-one or at 15-to-1 ratio at things called sections or recitations, at office hours and the like. And so what's keyly characterized CS50 in recent years has been the on-the-ground support structure and leveraging online technologies for what they are perhaps only best at. And to paint a picture of this, I thought I'd give you a teaser that we showed to our incoming freshmen just a couple of months ago called Pre-Frosh during Visitas. And the point of this video was to paint a picture of what the experience for students is like in this class, not only academically, but especially culturally. And you'll see a painter here picture painted of CS50 Puzzle Day, a start of semester event that tries to send the message to students that computer science is not about programming as they may see in secondary schools or assume from seeing their friends do it, but rather about problem solving more generally. You'll see a glimpse of the CS50 Hackathon, an event that starts at 7 p.m. and ends at 7 a.m. And it's an all-night opportunity, an epic opportunity, as we claim, to work on students' final projects at the end of the semester, which is a project of most anything of interest to them in software, followed by the CS50 Fair, which is a campus-wide exhibition of students' final projects in a couple of places, Harvard and Yale alike. So I give you CS50 in pictorial form. All right, this is CS50.
We've been wandering in the dark, a million miles apart, going nowhere. Believe that even if we're lost, you know it won't be long till we get there. We rise and we fall, we'll stay untouchable. Yeah, after it all, we'll stay untouchable.
Let me take a selfie.
Enjoying your friend and enjoying food.
Do it for
all very meta and a lot of pressure. I'm finding that Miles is tweeting about what's going on right now, so no pressure. The course now, I've been at the helm of the course now for 10 years, since 2007, and since 2007 have we made the course freely available to anyone online via OpenCourseWare, whereby all of the lectures, all of the sections, all of the problem sets, all of the infrastructure is freely available to students. But over the past year have we shifted our focus, continuing to make those same resources available, but now focusing all the more on teacher-facing resources. Indeed, in the US, as we've framed this, is CS50 AP in satisfaction of the College Board's new AP CS Principles curriculum framework. But the fact that it's denoted here as AP is only to piggyback off of that current initiative. It's not fundamentally tied to the AP course itself. Indeed, the course CS50 AP for high school students is curricularly and technologically identical to what we do on campus in Cambridge. In fact, the fundamental difference, and dare say the advantage that the high school students who have been piloting this program over the past year enjoy is a 36-week experience as opposed to just a 12-week or so semester. Indeed, that's been the key ingredient. This course has been offered at Miami-Dade College through Harvard's continuing education program and at Harvard and Yale, so very different academic environments. The key ingredient we found is to maintain the same level of expectations, to maintain the same level of rigor, but the secret ingredient is just to allow students a little more time, particularly adult students, particularly younger students who aren't necessarily full-time college students, to actually succeed ultimately with the requisite support structure in place so that they can work through it indeed at their own pace. And so what I thought I'd do quickly now is give you one final glimpse on video of the secondary school side of things. We had the opportunity a few months back to travel to New York City, CS50's team and I, where we met up with 8 of the schools currently in our pilot program with CS50 AP for a so-called CS50 hackathon. We had to time shift things. It wasn't going to fly to do it from 7 p.m. to 7 a.m., so we did the ungodly hour of 10 a.m. to 4 p.m. But nonetheless, it was a wonderful experience for the staff, and we hope for the students and the teachers as well, and indeed it brought students together for such an experience as this. Hello world, my name is David Malan and I'm an instructor for CS50, and we're here in New York City for the first ever CS50 AP hackathon that's brought together students from some 8 schools in the New York greater metro area to sit down for some 5 hours of the day with food and candy and friends and classmates and teachers and dive into CS50's problem sets.
Hi there, my name is J Malan. I'm just welcomed about 90 high school students, and they're all super excited about walkthroughs with J Malan.
This is the moment, tonight is the night.
Progressing through the problem sets, and they're all extremely interesting.
Making a code and actually seeing it being implemented, pretty awesome.
We're so excited to come down here.
We get to code, we get to, make these problems that can be beneficial to us in the world.
My name is David Malan, and this is CS50 in New York City. So ultimately the model we've adopted, or rather proposed to teachers, is that they consider either adapting or adopting the course's curriculum, either integrating small pieces of it as we have ourselves into the course's curriculum and into students' experience, or to lean on us to actually have students watch some of the course's online assets, but ultimately focus with students and focus their in-person attention on helping students get through the course's problem sets or programming projects. And to give you a sense of what goes on in our own classroom, as many students and teachers have now experienced as well, is perhaps this, a couple of vignettes, if we will, of what goes on in, say, our very first weeks of the class. So computational thinking is one of the emphases early on in the course, and we try to give students an appreciation that even if they're very, very uneasy about being in the course, they are among those less comfortable in the course's demographic. And indeed, at Harvard, some 72% of students last year had never taken a computer science course before, so they were very much indeed in good company, even if they might not have thought that. We defined for them in the first class computational thinking as just this. It's the process of taking inputs, so some problem that you have, passing them through some algorithms, some step-by-step instructions for solving some problem, out of which has to come outputs. And then we ask the question, well, what does it take to actually represent those inputs and outputs? Like, how do you model a problem? Now, most any student in the room probably knows or has generally heard that computers somehow only understand zeros and ones, the so-called binary system. But we ask then, well, what does that even mean? If you only have zeros and ones, how can you possibly compose things like letters on the screen or emails or or images or videos, well, we try to make clear to students that they're actually quite familiar with the concept of binary already at its core. And in fact, ultimately, we put a number of students on the stage, but we first show them, well, what is this pattern here? If I write down this number 1, 2, 3, this is just a pattern of symbols, 1, 2, 3, but we all immediately know it is 123. But why is that? Well, in our human world, we've long known this to be the ones column, or the ones place, this to be the tens column, this to be the hundreds column. And even though most of us, including the students in our classroom, might not have thought about a number like this in quite some time, surely it clicks quickly that, oh, right, it's 100 times 1, and then it's 10 times 2, and then it's 1 times 3, which of course is 100 plus 20 plus 3, which gives me 123 when I add those three things together. Now, it's built retro, although less so for students who are still in primary or secondary school, but if they're comfortable at least with this paradigm, we can very quickly say, well, the only thing that changes in the world of binary is that your alphabet, the number of digits you have at your disposal, are no longer 0 through 9, or 10 in the decimal system, but just 0 through 1 in the binary system. And so if we wanted to represent the number 0 in binary, we would still just do 0, 0, 0, and we don't need even those leading zeros, we'll make clear. But instead of the placeholders being powers of 10, we point out that they're just powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2, 8, 16, 32, and so forth. So now, if we want to actually represent information using just zeros and ones, well, how do we do that? This, of course, is 0, 0, 0, so that might be the number we know as 0. If I instead have something like this, 1, 0, 0, it's, of course, not in this context 100, but it's just 4 times 1 plus 2 times 0 plus 1 times 0, so that gives me, of course, 4 in the end, which is readily available. Of course, if we asked the students rhetorically now, or deliberately, how do we represent the number 7? It's, of course, 1, 1, 1, or what about the number 8? 1, 1, and now we have an opportunity to realize, how do I handle this? If I only have 3 placeholders, it would seem I can only count so high as 7 in binary if we actually walk through the intermediate steps there. And so it's an opportunity already to talk about overflow, or at least adding another bit into the equation. Now, if we are at this point in the story where students might grok this conceptually, well, how does a computer actually implement this? Well, we like to point out that at the end of the day, the only sort of physical input going into your computer might be this here power cord, or maybe the battery ultimately, out of which flow electrons in and out, somehow powering the device. So if we could if that's the only ingredient, how do we go from just this flow of electricity in and out to actually representing zeros and ones conceptually inside of the computer? Well, we point out that there's all these things inside of a computer called transistors, tiny little switches that we can turn on and off. And indeed, if they've ever heard of Intel or a CPU, which they might have, at least in the abstract, they might know that there's a lot of these little things inside of their computer. But each of those can just be thought of as something like this, like a little flashlight, whereby if I turn one of those switches on, I can represent a 1, and if I turn that switch off, I can represent a 0. And of course, if I have a second phone, if I might real quickly here borrow the source of our tweets, we have no more tweeting for a moment. So now with 2 light bulbs, literally, or 2 switches are that got fired. Now, we can actually count from 0 to 1 to 2 to 3, and of course, if I want to count even higher to 4, now I need a third phone, a third transistor, or a 4 and the like. Okay, it's a mile. So now we can stipulate that we at least now have some physical way of representing information. So thus was born the physical computers that we now have, and so we begin to talk perhaps at this point about abstraction, the fact that I don't need to care anymore how I represent the number 123 or the number 1 or the number 7. All I need to know is that I can represent it, and I can represent any number higher than that so long as I have enough bits, so long as I have enough transistors or ultimately memory inside of my computer. Well, one of the exercises we like to do in class, as is pictured here, is we actually hand students a whole bunch of sheets of paper like those here, where we just give one student the ones place, another student the twos place, another student the fours place, and simply inviting them to raise their hands if they want to represent a 1 in that place, or a 0 by just standing here more awkwardly. Do they represent a 0? And so we have this pattern of bits that we might spell out in front of their peers, not pictured here in this context, of course, is 800 of their classmates. So it's a bit of an uncomfortable situation for some, although there's certainly enough students in the audience who are eager to come up and volunteer in this way. And so we might spell something out. using either human volunteers, as we do there, desk lamps. On a whim one year, I ran to Target, like a Walmart-like store, to buy some very inexpensive desk lamps that we used before everyone had cell phones readily accessible in the audience, perhaps. But also, could we do something fancier still? We sort of raised the game a couple of years ago, and one of our undergraduates actually built for us what we now call binary bulbs. So if you've ever seen the Philips Hue light bulbs, these are light bulbs that you can put in your home, but they have an API. And they also have iPhone and Android apps and the like, but also an API that you can program against. And so one of our more industrious students actually wrote a piece of software via which, on a web page, or in turn an iPad, to turn the light bulbs on and off by just pressing buttons on a screen. And in this way, did we now have a much fancier, unfortunately a much more expensive version of our binary bulbs, but amortized over the past several years, it served us well, and we did at least economize on the placeholders. Those are just little refrigerator magnets. So a fun dramatic flair to add is to just wipe them all off just after someone has volunteered to come on up and actually solve some binary game. And in fact, we have a digital version that's freely available online too that we embed into the course's own homeworks today, these days, called Binary Bulbs. And indeed, if we wanted to have someone play a game here, you might click, for instance, if I switch over to the interactive version of this game mode, I might want to represent the number, say, 7, click OK, and now students on their own for homework or in class as a demonstration can simply come up and do the digital equivalent of clicking on the bulbs, turning them on and off, and they get a little clue here as to what the value represents, and if they actually do get 7, all of the bulbs start blinking, just like the physical bulbs that we have in class. But this has made it much more accessible to anyone to use in their own classroom. We can then maybe very quickly turn the bulbs off and make this equivalence. These light bulbs are really just zeros and ones. This might look more arcane, but the idea is exactly the same. And we can really step things up by turning off the labels altogether and allowing students an opportunity really to sort of challenge each other or by way of this binary game. So beyond that, we then shift. Once we have the expressiveness of binary and decimal and so forth, and if you'd like, as an aside, and I'll make these slides available afterward, at cs50.ly/bulbs is that example, we then start to abstract on top of those number systems. And we say, well, if you want to actually represent text now, or send an email, or write an essay, how do we actually store that kind of information in a computer if all we have are zeros and ones? And so we claim to students that, well, we simply have to stipulate as humans that just some arbitrary pattern of ones and zeros, or some arbitrary number is going to represent capital letter A. You know what? It's going to be 65. And if you want to store the letter B in your computer, it's going to be the number 66, and so forth. And then once you have the mapping, or ASCII in this case, from numbers to letters, can we actually spell something out? So for those quite familiar with ASCII, or the photographic memory, what have we spelled out here? It's okay. This is not this kind of thing we put on the quiz. It's really meant as an in-class exercise. 72, 73, 33. So it's just high with a deliberate corner case, whereby the exclamation point is not pictured, but it might still appear on a keyboard and therefore have some code. But more fun is another example that we sometimes do besides high, which is to actually put up this one here, 66, 79, and 87. And what we similarly do in this case is we actually have 8 volunteers come up on stage, or you can get away with 7-bit ASCII if you only have 7 volunteers. We hand them each a cheat sheet that tells them that they're about to participate in 3 rounds of binary. And they either in round 1 need to raise their hand or stay still. In round 2, raise their hand or stay still. In round 3, do the same, based on the pattern that I've preordained on the sheets of paper. And what they end up spelling out in binary is first round, 66. And then we ask students, all right, if it's 66, what did your classmates on stage just spell out? B. And then we say, all right, we have everyone raise or lower their hands representing the number 79, at which point people in the audience realize, oh, it's B-O. And then we do it one more time and say, all right, the pattern of bits, as they do some quick arithmetic, is 87, correctly or incorrectly. Sometimes we coax them toward 87, because they're seeing, again, the binary version, not the decimal version. And, of course, 87 gives us W. So now we have this very grand opportunity for everyone to take a bow in front of the room, except when someone shouts out that it spells bow, which breaks the whole demonstration. But it's been a nice little climax to a fairly simple exercise that's unfamiliar to students at the outset, but after just a half an hour of the first class, do they realize, like, oh, I've learned in just the span of an hour how binary works, even though they might still need to wrestle with it a little bit, and just that ASCII, or whatever you want to call it, exists, that it's just this mapping from numbers to letters. And so we transition from there to abstracting away further. Well, how would you represent a color Well, some kids, especially if they tinkered with their Mac or their PC settings, might have somewhere noticed RGB, red, green, blue, even if they really never thought about what that acronym means. But if a computer simply has some amount of red and some amount of green and some amount of blue used to paint every one of the dots or pixels on a screen, well, we could combine those numbers together just as though they're bits, so as to represent the color of a dot using just, in this case, 8 plus 8 plus, or 24 bits. And we would go into a little more detail. We're rather flying through right here. But with 24 bits, could I say, give me a decent amount of red, a decent amount of green, and not too much blue? And if you combine those three shades, what do you get? You get this, unfortunately, this murky shade of orange, or brownish, which is the pictorial equivalent of high, exclamation point, unfortunately. But now we can stipulate that we have a way of representing colors or dots on a screen. So how do we represent an image? At this point in the story, well, an image is just a grid, like width and height of a whole bunch of pixels. Well, what's a movie or a video that you're watching? Maybe it's just 30 images every second flashing in front of you. So we've already gone in the first hour of the class from zeros and one and transistors to how you might represent something like a video. And so we emphasize one of these key concepts so early on in the class, like abstraction. But of course, we've gotten ahead of ourselves. But we now have a representation of inputs and outputs, binary at the end of the day. We don't really have to worry too much about that. What about algorithms, that third and final ingredient we claim to computational thinking? Well, what's that all about? Well, back in the day, we had phone books in America. These are getting increasingly hard to find, so much so that I couldn't find one here in the UK. And so very kindly loaned to me on the condition that I not tear it apart is this here dictionary. With which students might be more familiar, but indeed at home, when we do have a stash of dictionaries, of phone books, do we use this as an opportunity to talk now about an algorithm? Because indeed this word, though unfamiliar semantically to students, is conceptually probably pretty familiar. If it's just step-by-step instructions for solving some problem. So we might ask in class, how would we go about finding Mike Smith? And for the sake of demonstration, I'll pretend that this is a phone book, only because it lends itself to more drama if it were actually as suggested here. But if I'm looking for someone like Mike Smith, we might ask the students, well, how do we find him? I could just start at the first page and look at page 1 and see if Mike's there. If he's not, page 2, page 3, and then might ask, is this process, this algorithm, correct? Yeah, so there's a little disagreement, it seems, but it is correct. But I heard over here it's correct, but it's not efficient, certainly. If Mike's here, I'll eventually get to him, well beyond our patience here. But if I go one page at a time and Mike Smith is in this phone book and it's alphabetized as I expect, I'll eventually get to the S's, and indeed Mike Smith will be there. But of course, I learned in grade school that I don't have to count by ones, I can count by twos. So I might go 1, 2, 2, 4, 6, 8, 10, 12, and so forth. Now that algorithm is faster, kind of sounds faster, although it's physically harder to do, it seems. But is it correct? Why is it not correct? Yeah, I might miss some. I might just get unlucky, and when I turn 2 of those pages, damn, Mike's right in the middle of the 2. But that's a possible fix. I should just make sure that maybe once I hit the T section, T coming after S, I should double back at least 1 page. And if I were really precise, I could indeed look back maximally 1 page. So an opportunity eventually for us to talk about conditions or branches where we actually have a little bug fix there. But of course, none of us are going to search for Mike Smith or a word in the dictionary in that same way. What is most any intuitive human going to do? First of all, they're going to take out this device these days. But they're going to flip probably roughly to the middle, give or take, and then I say, oh, I'm on the M section. Now in class, I'm not allowed to do this today, I would, as best I can, tear the problem in half, both figuratively and literally, dramatically throw half of the problem away, and then fundamentally be left with really the same problem. It's a smaller problem, it's half as big, but it's fundamentally the same problem, and key here is that the algorithm with which I can now find Mike in this latter half of the phone book is exactly the same. I can go roughly to the middle here, darn it, now I'm in the T section, but here too, could I tear the problem in half again, throw it away, leaving me with a problem that's now a quarter of the original size. So I claim maybe we started with 1,000 pages, now we're down to 500, to 250, to 125. We're really taking big bites out of this problem, much bigger than just 1 or 2 pages at a time. And so we could transition from here then, talking about ultimately we have just 1 page. We talk briefly, even in the course's first day, about what the relationship between time and the size of the problem here might be. And we don't necessarily introduce things like linear or logarithmic this early on. That would be optional at this point. But the shape of the curve is something we would introduce even this early on. But then we ask students the question, how would we actually translate this intuition to code or programming code? And we might do it in this way. Step 1, pick up the phone book. Step 2, open to the middle of the phone book. Step 3, look at the names. 4, if Smith is among names, call Mike. Else, if Smith is earlier in the book, open to the middle of the left half of book, go to line 3. Else, if Mike is later in the book, open to the middle of the right half of the book, go to line 3. Else, give up. But we use this as an opportunity to point out a few defining characteristics of most any imperative program. Well, we have these statements or procedures or functions like lines 1 and 2 and 3. Just do this. They're just actions. In steps 4 and 6 and 9 and 12, we seem to have something fundamentally different, which is like the proverbial fork in the road. 4 different things might be ahead of us, and so we have to decide to go this way, this way, this way, or that way. And we point out already that many languages would literally indent the words beneath to make clear that only do this indented line if it makes sense based on the branch that you've taken. And there's even a loop. It uses more of an older school approach, but one that's very easily understood by anyone even unfamiliar with programming. Just go back to line 3. And we could implement this any number of other ways using perhaps more code-oriented constructs if we might like. But what we ultimately do in the class, in fact in this very earliest of time, is to then get students very involved. And so we point out, after this algorithm here, what if we defined another algorithm still? And in fact, if you would humor me, this one is a 3-step algorithm, but it requires a little bit of audience participation, non-speaking roles. But if I were to take attendance in this room, how might I do it? You could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we already learned there's a faster way. 1, 2, 4, 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. But could I do even better? Well, I can if I leverage some parallel processing, if you will, multiple brains or computers in this room. But to do that, I need to program you in parallel. And if everyone wouldn't mind humoring me with just step 1 by literally standing up and assigning yourselves the number 1. I have volunteered Miles, if he doesn't mind, to do it the old school way, so we'll see who wins. Step 2 now for everyone is pair off with someone standing, add your numbers together, and adopt the sum as your new number. Okay, at this point in the story, everyone should be thinking of the number 2, except maybe for one person if there's an odd number. So step 3 is one of you in that pair should sit down. The other should go back to step 2. Those of you still standing should realize now you are now in a loop because you have been instructed to go back to step 2. So if you would, pair with someone else still standing, add, sit, repeat. So theoretically, there's only one person standing at this point. But that's okay. If you're, I'll help with the finishing the math. So what number are you still thinking of? 7. So you are thinking of the number 7. Okay. Okay, that would have been 8. Okay, that's okay. You can both sit. What is your number? 16. You can sit down. 8. And you may sit down. 21 and 8 and 41, and anyone, 32, anyone else still standing? All right, so according to this algorithm, you may sit as well, there are 134 people in this room, according to the algorithm I claim is not only theoretically correct, but much, much more efficient. We could liken that algorithm to even the binary search or the division and conquering that we did of the phone book. Because what's powerful there, even though I kind of cheated in this case by leveraging all of you as opposed to just doing it myself or just Miles on his own, we were still fundamentally doing the same thing. On each iteration of that counting algorithm, did half of you, theoretically, sit down, and then another half, and then another half. Which is to say, if there were something like 1,024 people in the room initially, we suddenly went to 512, then 256, then 128, and so forth, with half of the room sitting down at each time. Put another way, if suddenly another 1,000 people tried to cram into this room, thereby doubling the population from 1,000 to 2,000, you might ask the question, well, how much longer is it going to take Miles to count everyone? He might have spent 1 second or so per person, 1 unit of time per person, so it might have taken him 1,000 seconds initially. If 1,000 more people come in, it's going to take Miles 1,000 more seconds because the number has doubled. But of course here, assuming everyone sits down per the algorithm, that additional 1,000 people is going to be handled with just one iteration of that loop. And if we really consider that iteration of the loop to just be one bigger step, one bigger second, it's going to take just 1 additional second to count those additional 1,000 people. It's going to take 1 additional second to find Mike Smith in a 2,000-page phone book. And that's when then intuition suddenly becomes powerful and also very familiar, we hope, to students. And again, can we raise a discussion like this to actually give them a sense of the feel for the shape and to actually introduce even a little bit of mathematics here to explain and to describe what we've seen as opposed to just introducing the terminology for itself. Now, allow me to use our final minutes here together to do the demonstration that we like to do that I claim that I discovered from my 5th grade homeroom teacher who used it at the time to teach us how to follow directions and in turn listen to her. And most every one of my colleagues in the CS department has claimed since that they have been doing this for years in their CS classes. So I don't know where it started, but I can go as far back as 5th grade in my personal case. This is perhaps a familiar animation you might have seen, or if not, some student will perhaps bring it to your attention at some point. It's an opportunity to do this. Now, I have been told there's signs on the door that there is no eating or drinking in this room, but there is no sign disallowing us to make sandwiches in this room, so long as we don't actually eat them. To do this, though that's never a problem anyway, based on how they come out. So for this demonstration, we just need 3 volunteers. Not 1,000, but 3. If could get some brave hands. Okay, 1 in back there. Phil Bagg, I'm told. Phil Bagg, I'm told, has brought jam to the UK. So please, Phil. And one other, maybe farther back. Come on down. Yes. Yep. You're the next contestant. The Price is Right. And what we have here, thanks to our kind hosts, Helen and others, is we have 3 plates. We have 3 loaves of bread. I do gather jam is more the norm here, but we did this the Americanized way with some peanut butter and jelly. Come on forward. Let me set you up. We also have the fortune here of 3 jars of peanut butter. Here we have some strawberry jam, so that's our connection here. All right, 1 and 2 and 3. 3 knives and no napkins. So here we are. So while the opportunity at hand ultimately is meant to have a bit of fun with students in a class, particularly toward the end of the class where we want to re-energize, ultimately we're trying to send a message with this kind of a demonstration as to how precise you need to be when programming a computer and how a computer really, as intimidating as it might be to some students, is kind of a dumb device that's only going to do what you tell it to do, sometimes quite literally. And so with our 3 volunteers here, if you'd like to introduce yourselves.
Hi, Catherine.
Sandwich bought 2,000.
So, let me go ahead, and I'm going to go ahead and open up a little cheat sheet here. I will just play the role of scribe as you, the audience, if you would, program these computers to make us one, and only one successfully, peanut butter and jelly sandwich. Step 1, if someone would, please.
Open the bag.
Open the bags is what I heard. Terribly precise. Open the bags.
Don't know which hand to open bag with.
Would someone like to elaborate? Open the bag. Open the bag. More precisely?
Catherine, take out 2 slices of bread.
Okay, this program's now just for Catherine. Catherine, Take out 2 slices of bread. Next step. Place bread. I heard table and plate, but I'll go with plate.
Is that still casserole?
Would someone like to catch us up here? Step 3. Open the jam jar. By this point, the students would have realized that the earlier instructions were not precise enough, so we should be a little more precise. Open the jam jar by twisting lid. Counterclockwise. Counterclockwise. While holding it with the other hand. This is like a room full of like that students who. Step 4. Remove lid. Pick up the knife by the handle. Step 6. Put the lid down. Put the knife in the jam. Put the knife in the jam. Step 8. Pour it down. Pour. I hear use knife. Scoop some jam. Step 11. Stop. Sorry. We did the videos for 10 years, and it has never gone this wrong. Okay, step 12. Let's take it home before we introduce Miles. Step 12. Sorry? Ask a friend to make me sad. Why don't we end it there? Thank you to our volunteers. This is ridiculous. Thank you. This was just a glimpse of what we do in Cambridge. Thank you so much for having me.
Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.